This module will introduce the basics of form finding in Grasshopper using Kangaroo library. The module is divided into multiple chapters, with simple and engaging guided exercises designed to explain the various goals and constraints available in the Kangaroo library. Before we dive into Kangaroo, let's understand the relevance of form finding. Patrick Schumacher describes it as a physical setup where form self-organizes and is not drawn by hand or invented or preconceived. It emerges out of a natural process. The oldest documented method of physical form finding is the reverse hanging model used for designing arches, vaults, and shells. It is a physical model with elastic cable or membrane with no rotational stiffness, subjected to gravity forces, to obtain a structural state of pure tension. Such form is called funicular, which is then inverted to identify the mechanical compression-only situation. Robert Hooke first proposed it in the 1700s, where a reverse curve generated by hanging a chain under self-weight and supported only at its ends, to define the optimal structural form of an arch. Such a curve is called catenary, not to be confused with a parabola. Frei Otto used the same principle to find the structural form of reinforced concrete or masonry vaults, shells, and steel or timber grid shells. His technique takes advantage of non-rigid nets under gravity, custom loads, and fixed boundary conditions for form finding. The multi-hall in Mannheim is probably the most recognized building designed with this method. Other form-finding experiments such as stretched membrane under pressure and soap bubble models led to notable projects like the German Pavilion of Expo '67 and the design for the Stuttgart station proposal. Today, traditional form-finding techniques are applied digitally using particle spring systems that simulate the physical behavior of deformable forms. Initially developed for character animation and cloth simulation, particle spring systems have emerged as a powerful technique for form finding. Whereas traditional methods were difficult to apply, digital simulations allow designers to investigate form, in real time, by updating forces, supports, and physical properties. From a conceptual standpoint, it also provides freedom to look beyond the limits of physical form finding, which is always directed towards the structural optimum. Kangaroo is a library and set of Grasshopper components for form finding, physics simulation, and geometric constraint solving, developed by Daniel Piker. In recent versions of Rhino and Grasshopper, Kangaroo is available as a default library, and its features are accessible within Grasshopper. This diagram explains a typical Kangaroo workflow, highlighting the three critical steps: geometric discretization, goals, and solver. A particle spring system discretizes a continuous model into a finite number of masses, called particles, connected by perfectly elastic springs. It requires geometric input in the form of points and lines to simulate various constraints. It also works with meshes since the topological structure is defined using vertices and edges. Hence, the first step in Kangaroo workflow involves discretizing the form to relevant points and lines for initial input geometry. The constraints applied to these points and lines are called goals. Essentially, a goal can be understood as external forces, any function that displaces certain points to a new location based on its current position. Kangaroo contains many different types of goals, which can be applied in any combination, and Kangaroo will compute the goals to meet them all. If the goals conflict with each other and no simultaneous solution to all of them is possible, the points will find a compromise between them. More specifically, it will minimize the sum of their weighted squared distances from their targets. Each goal can be assigned a scalar value for its weighting or relative importance. Kangaroo Solver is the component that collects all the goals, and solves the system. The solver automatically runs until the goals converge. All the forces reach a geometric equilibrium and then stop. For simple setups, this can be pretty much instant, so you will just see the equilibrium result. For larger or more complex sets of goal objects, it will display the current state every 15 to 30 milliseconds approximately. That's the typical Kangaroo workflow. In the next chapter, we will set up our first Kangaroo definition.